Thank you. All right, good afternoon, everyone. We're going to get started. So thank you all for coming to the Data Matters seminar series. Today it's my pleasure to welcome Jonathan Pober, who's an assistant professor in the physics department. And Jonathan uses radio telescopes and big data to study some of the oldest and biggest things in the universe, galaxies. And so I first met Jonathan about 3 years ago when we connected about using machine learning. And I quickly realized that Jonathan works with data sets that dwarf many of the ones that we use in other areas of machine learning, like natural language processing and even computer vision. So just this week, a student that we co-advise said to us, oh, I generated about 55 terabytes of data this week. And that's more than the rest of my group has collected in the 4.5 years that I've been here. So there's a lot of fascinating stuff in Jonathan's work, and I'm really glad that he's agreed to come and share that with all of us. So with that, I'll turn it over to Jonathan. Let's welcome him.
Thank you. Get this set up. All right, great. Well, thank you again. It's a pleasure to be here. Really happy to have a chance to speak about this work and try and give you a sense of what the problems we are struggling with in this field of cosmology and astrophysics, and where data analysis is, well, at the forefront. So before I start, I want to give an acknowledgement that I work on large experiments with many, many collaborators. This is just a small subset of the people I've worked with. A lot of students at Brown have gotten involved in this work. They're the italicized folks. Well, Steve's, you're italicized too. Not a student, but it looks like we're on autoplay, so I got to go fast. I also want to acknowledge that we're on the ancestral lands of the Narragansett tribe here at Brown, and that the MWA, the telescope where I do most of my research, is on the traditional lands of the Wadjuri-Yamaji people in Western Australia, and they're the traditional owners of that site. So for an outline of this talk, as I said, we've got a lot of time for Q&A afterwards. I don't want to give a particularly long talk, but I've highlighted, I think, 2 M's and 3 I's. I want to give kind of the motivation of what we're doing and describe the measurements that we make. I think that can feel a bit technical at times, but it's important to get a sense of what do we actually measure to understand what our data are. And then I've identified 3 challenges that I think data science, machine learning, other aspects of computational modeling can really make a difference. I would be lying to you if I said these are the only 3 challenges in my research, but I think these are 3 good ones, 2 of which I'm working on with Steve, and 1 of which I'm really interested to know if anybody has any ideas on, because it's hard. And so what are we trying to measure? What's the big picture here? And so for the motivation, I grabbed this chart. This is known as the standard model of particle physics. And so this is what my colleagues working on particle accelerators and fundamental physics theory think everything is made of. What is the most basic structure of matter? And you may recognize some of the particles here. There are electrons, photons, that's light. Protons and neutrons are missing because they're actually composite particles made up of these quarks. And then there's a lot of other exotic particles. But this chart, and in particular this Higgs boson at the middle, which was sort of the last discovered in an experiment, this really represents an incredibly complete understanding of what matter is made of. Decades and decades of work, huge experiments, particle accelerators. This model has held up to every single test. It's incredibly well validated and with an incredibly strong theoretical underpinning. But if you ask an astrophysicist what is the universe made of, they'll show you something like this, that about 5% of the universe consists of ordinary matter. That's everything described here. But 27% of the universe is some particle, possibly not even a particle, but we call dark matter, something that does not interact with light, but interacts gravitationally. And so we can see its effects on the growth of structure in the universe and lots of other astrophysical situations that just can't be explained without dark matter. Even more puzzling is dark energy, contribution to the energy density of our universe that's governed its expansion, we don't know what dark energy is. And so there's this fundamental mismatch. As I said, this standard model of particle physics is an absolute triumph of the last century of physics. It's incredibly precise, incredibly well-founded, and yet it describes what we think only makes up 5% of our universe and makes no predictions for what could be dark matter and what could be dark energy. It's complete. And yet it doesn't predict those two things that we're very convinced exist. And so there's a big question here that astrophysical observations that have led us to believe that dark matter and dark energy are real, what are they? And so astrophysical observations are still one of our main ways of trying to identify the detailed properties, the fundamental nature of these dark constituents of our universe. What I want to observe is hydrogen. Hydrogen is ordinary matter. We can't see dark matter. We can't see dark energy. So we need to look for their indirect effects on ordinary matter. And if you're going to observe ordinary matter in the universe, hydrogen's a really good choice. 75% of all the ordinary matter in the universe is hydrogen gas. It's the simplest atom. It's a proton and an electron. And the way we study it is with what we call the hyperfine transition, which is a fair bit of jargon. But the idea is that quantum mechanically, so here's our hydrogen atom, a proton and an electron. Quantum mechanics predicts that particles have an intrinsic angular momentum we call spin. And they can be spin up or spin down. There are two states. And there's a very, very small energy difference in the hydrogen atom when the proton and the electron are both aligned with their spins versus anti-aligned with their spins. And so if you're a physicist, you have tons of different ways you think about energy, electron volts, temperature. As a radio astronomer, I think about this in terms of wavelength. Light comes out, a photon comes out. When the hydrogen atom goes from its higher energy state to its lower energy state, a photon of wavelength 21 centimeters is emitted. That's a radio wave. We can detect that radio wave and map out hydrogen. And so that's what I want to observe. Map out hydrogen, use it to understand the properties of the universe. So here's a simulation of what a huge chunk of our universe looks like through the lens of hydrogen. So these axes here, this unit megaparsec is an extremely large scale. This is 1,000 megaparsecs, so a gigaparsec on a side. This is an enormous fraction of our universe, a computer simulation of an enormous fraction of our universe. And it's what the hydrogen would look like. And as I said, we want to study this distribution and uncover the physics that's encoded in this map. And so we're going to do that with a radio telescope. This is one antenna of the Murchison Wide Field Array, the MWA. There are 256 of these. Each antenna is actually made of 16 smaller antennae compiled into what we call a tile. You maybe can't see it here, but there's a sheet of chicken wire sitting underneath it that connects them all electrically. And we want to use these radio telescopes. It doesn't necessarily look like a telescope, but it's how we measure radio waves. And we want to map this volume. And so we can do that in 2 dimensions the way you think of making maps. Make a picture of the sky. Map your telescope. And in these x and y directions, get a picture of what the hydrogen looks like. But what's really promising about this technique relies on an important piece of cosmology. And so the idea is that this depth axis corresponds to a measurement versus frequency, or wavelength. They're equivalent for electromagnetic waves. And let me explain why. So the universe, we believe, has been expanding since the Big Bang. The universe started out very, very small, very, very hot, very, very dense, and has been expanding ever since. As the universe expands, light traveling through it stretches with it. And so if a hydrogen atom, way back in time when the universe was half its current size, if that hydrogen atom emits one of these 21 centimeter wavelength radio waves, as it travels to us, it stretches along with the universe. And by the time it gets to us, it'll be 42 centimeters. said it was emitted when the universe was half its size, and so it doubles in wavelength. And so if we can measure all the possible wavelengths that this hydrogen signal could be stretched to, starting with 21 centimeters here at the front, going back to upwards of 20 meters at the back, stretched, emitted when the universe was something like 1/100th its current size. If you can build a telescope that measures all those wavelengths at once, you can convert them to sort of a time or a distance axis. Signals coming at a lower frequency were emitted earlier in cosmic history. And that's why in the simulation, you see the signal evolves along this axis. It looks different at the back than it does at the front, because we're actually probing a different time in cosmic history. And so this is the promise of this technique, a 3D tomographic map of the universe, not just one map, but that frequency axis giving us the evolution of the universe, the depth direction. The problem is, it is not the only source of astrophysical radio waves. Between us and this distant hydrogen we want to observe are all other sorts of radio emitters. So here's a map of the Milky Way in radio waves, right? So that's the plane of the Milky Way running down the middle. The center of the galaxy, where you may know there's a supermassive black hole right here at the center of the map. Now, off here, it looks like the signal's weaker, but even down here, the emission from our Milky Way and all the other galaxies in the universe dwarfs the hydrogen signal by 4 to 5 orders of magnitude. It's a 1 part in 10 to the 5 additional signal on top of all these other astrophysical foregrounds, we call them. Right? They're foregrounds because they're between us and the signal we want to measure. As I said, the foregrounds are incredibly bright, 4 to 5 orders of magnitude brighter than the 21 centimeter signal. The hope that we have for this field is that we understand the physics that makes the foreground radio emission. You can take a graduate level course in radiative processes and astrophysics, learn about the mechanism that leads to these photons being produced, and conclude that as a function of frequency, or as a function of wavelength, their spectra are distinct from the hydrogen signal. The foreground spectra are smooth, so they don't change much from frequency to frequency. Whereas that hydrogen signal, remember, every frequency was a little different depth through that cube, and so there's a lot of structure in the hydrogen signal versus frequency. And so that's how we can hope to separate these. We're looking for 1 part in 10 to the 5, little bit of structured frequency signal on top of this incredibly bright, smooth background. And that's doable. It's hard, but digital signal processing has come a long way. If you gave me a box and said I put some hydrogen signal in here and some foreground signal in here, separate them, I'll do a Fourier transform in Python and I'll have them separated for you in a couple minutes. So this is doable. What makes it so hard? I haven't mentioned, I've been working on these experiments since I was a PhD student. That's about 15 years, and we still have not detected the hydrogen signal. I've been working on the same project for 15 years.
You haven't?
We have not detected the hydrogen signal. We have not separated it from the foregrounds. We know it's in the data, but we have not managed to clearly separate it from all these other contaminants. And so, as I said, I'm going to highlight 3 challenges. In 15 years, we've worked on more than just 3 challenges, but these are 3 that I want to focus on today. The first is this idea of identifying contaminated data. Pardon me for a moment. And so I mentioned that astrophysical radio sources are a big problem. Human-generated radio sources are a big problem. We make a lot of radio waves. This 2-meter wavelength range is FM radio, digital TV, satellite transmissions. They're all in this band. And we have to observe despite them. They're so bright that they just have to be excised from the data. If there is a radio transmitter transmitting when we take our data, that data is not usable. So we build these instruments in these very remote sites like Western Australia to get away from tremendous amounts of human-generated interference. But you can't get away from everything. 5 years ago, I would have told you this was pretty much a solved problem, though. These human-generated signals look quite distinct. So here's an image from the Murchison Wide Field Array. This is one way of looking at our data. This is time. This is frequency. And so this is a 146 megahertz signal getting stronger and stronger and stronger. That's ham radio. A very nice algorithm written by Andrei Offringa that we now call A.O. Flagger in his honor, I suppose, goes in and finds these signals. These horizontal lines are expected. They're a feature of the instrument that we don't want. But it very clearly identifies this signal and tells us don't use those frequencies at these times. And this A.O. Flagger formed the basis of pretty much all of our work that discarded these interfering signals. And so it was only the work of a PhD student, Mike Walensky at the University of Washington, that really said, well, what if there's signals that are fainter than what we can see in 2 seconds, right? This, or 2 minutes, but much, much brighter than that very, very faint hydrogen signal. And so this is an example of such a signal that he found. This is digital television reflecting off an airplane as it flies over the site. Right, so the site's very, very far from any digital TV transmitter. It's below the horizon, but it goes up, it hits, and I think this is actually a bush plane, not even a commercial jet. It's going too slow to be a commercial jet. Bouncing off of it, reflecting into our telescope. And so we needed to have new techniques that could find this stuff. The traditional techniques could not find this. And so those techniques have been developed. What you have to do is you have to integrate your data in some way. If something is below the noise level, you need to average things together to make the noise go down. You need to average it in a way that the radio frequency interference doesn't go down. And so there are some axes that we expect radio frequency interference to be constant over. There are some we don't. And so you have to pick that averaging wisely. And that's the work of Mike Walensky in his PhD thesis to show a way to get much more sensitive measurements. But why stop there? We got a lot more sensitive with that, by seeing digital TV reflecting off airplanes, but what about digital TV reflecting off Starlink? We expect that will still be brighter than the hydrogen signal, but not bright enough to be detected with the algorithms we have. And so new algorithms are being developed, new way to find radio frequency interference, and as this has grown, in talking with Steve, we kind of identified a new problem, which is that when you have half a dozen different ways of identifying radio frequency interference that don't agree with each other, that some are going to find some signals, some are going to find other signals, you get different answers if you run one first, the other second, versus the other order, because they change the statistics. These are all statistical algorithms. How can we make them behave self-consistently? And so this is work that we're starting now, and this is a diagram from Steve, to basically take all these specialized RFI flagging mechanisms, build a weakly supervised machine learning framework that learns from the flags and can resolve conflicts between them and give us a better ground truth set for training in the future. That we have no ground truth. We don't know what RFI is in the data. We can go look for it by eye, but it's not ground truth. And with the volumes of data we have, that doesn't get you very far. And so this is a very promising approach for taking us to that next level, building a framework that uses all of these algorithms consistently, and maybe can help us find the next fainter level of signals. So that's challenge number one. Challenge number two is what I think the hardest problem we face right now is. This is modeling our instrument. And so let me explain why I think this is such a problem. So here's another view of part of the MWA. As I said, one of those tiles, it's actually consists of 256 of them. Here's 36 in one image. They're spread out over kilometers. We do not make images of the sky with this telescope. What we measure are complex correlations of the voltages from each pair of antennas. You take this antenna, you send its signal back to a supercomputer. You take this antenna, you send its signal back, you correlate them. And you do that pairwise for every single set of antennas in the array. And those correlations can then be used to reconstruct what the sky looks like. In the textbook on interferometry, imaging is chapter 11 on page 800. There's a lot of work that goes into actually taking these voltages and these correlations of voltages and turning them into a picture of a sky. But we know what they are. We know how they're related to the sky. And so I put this scary looking equation up mostly to tell you I can write down the relationship between what I measure and the sky. Right, so this I here of theta and f. Theta is angle, that's direction on the sky. F is frequency, which I said that's going to give us the depth direction of our cube. That's what we want to measure. We want to know what the sky looks like as a function of angle and frequency. This Vij, where I and j are indices basically counting our antennas, so the visibility, we call it, from antenna 122 and 123 is given by this equation. As I said, it's related to the sky with complete accuracy. There's no approximation in this equation I wrote down. The problem are these terms that depend on our telescope. And so even this equation is not invertible. I can't just take my measurements and in a single line go to what the sky looks like. But there's lots of ways to solve a known but non-invertible equation. A former postdoc and former graduate student that built a very nice Bayesian pipeline for MCMCing through the visibilities and getting a reconstruction of the sky out of it as one example of how you might solve this. But we can only do as well as we can constrain these properties of the telescope. And so let me tell you what they are. This first one, Rij, that's the separation between antennas. What's the distance between antenna I and antenna J? That one's not too hard to measure. You go out there with a sort of laser ranger, you make some careful measurements, we have a pretty good idea where our antennas are. And lesson learned from my PhD thesis, we no longer build antennas that can move when it gets really windy. So Rij we have a pretty good handle on. This B, we call it the primary beam in our jargon, but it's the response of the antenna to electromagnetic radiation from different directions and different frequencies. And so what I mean by that is if you think of a satellite dish and it's pointing straight up, it's going to see radio waves coming straight down into it, but it's not going to be anywhere as sensitive to radio waves coming in from the side. And so this is a map of that sensitivity pattern versus frequency. Knowing it at the level of accuracy that we need to know it is very challenging. You can build a very good electromagnetic simulation. There's software out there that basically you tell it exactly what your metal looks like, how they're connected, what angles are between them, and it will tell you this B. But then you deploy these out in the desert, leave them there for a decade, let them heat up and cool down, let lightning strike your array, and this starts varying from antenna to antenna. And we have no way of in situ measuring this with anywhere the precision that we need. And so that's something, we're working on techniques to measure this in situ, but those are hard. But the worst part are these Gs, the complex gains of every antenna. So every antenna, to convert a radio signal incident on it to a voltage that's actually measurable, has an amplifier in it. That amplifier is different at a very, very small level, but it's different from antenna to antenna. That amplifier can also cause a very small delay. We're sensitive, very sensitive, to if the signals from one antenna arrive at the computer a nanosecond later than a signal from another antenna. That has to be calibrated out. And so these change also from antenna to antenna like the beam, but they also are going to change with time. They're very sensitive to the ambient temperature. And when your array is in the desert spread over 5 kilometers, half of it might be behind a cloud, half of it might be getting baked in the sun. And so the time variability of these gains spend a lot of time trying to figure out how to capture what's happening directly from the data. That's the only measurements we have. And so we can say, right, our data comes from the sky and the telescope. We need to figure out which part came from the sky, which part was put there by the telescope itself. And so there's a lot of open questions here, right? Starting from the more traditional questions that someone in my field would ask, right? How can we more accurately measure these? I'm calling them nuisance parameters because they effectively are. Yeah, sorry, question?
These antennas interfere with each other, so radio wave is reflected by one antenna to another antenna?
Yes, so what we call mutual coupling or crosstalk. They're a related but different phenomenon where the presence of another antenna changes the beam of one antenna, or a signal can go into an antenna, run into an impedance mismatch, that your cable wasn't quite tight enough, reflect, come back out, and wind up in the other antenna. There's lots of effects at that level that
And you can disentangle these.
we would like to be able to disentangle those. But that's another complicating factor to determining, in particular, this B here. So as I said, traditionally we would ask, how can we more accurately measure them? What techniques can we come up with to measure them better? What I've started asking is, how can we deal with the fact that we're never going to know them well enough and actually incorporate uncertainties on them into our analysis pipeline? You can write down the right way to do that, but with our data volumes, computationally, we haven't been able to actually make it happen. And so lastly, this is my way to try and put this question in a data science language. How can we, directly from the data, solve for these parameters and or marginalize over them? And are there weakly supervised methods that can, given our data, which we have lots and lots and lots of, I think we're at about 40 petabytes sitting in Western Australia right now, can we disentangle the sky from the telescope? Very much an open question. And so the last one, yeah, of course.
The computational challenge in finding I is that, does it boil down to some kind of gigantic linear system inversion problem that you're trying to solve there, and then propagating the uncertainties through that?
Yeah, and it's not necessarily completely invertible. If you don't have enough V's, there's fundamentally properties of the sky you did not measure and have infinite possible values. And so this last question, and this is something I'm working on again with Steve and our co-supervised PhD student Jasper. Let's imagine a wonderful future where we've solved all these problems and measured the hydrogen signal. How do we actually get science out of it? So here's this simulation again. How do we go from measuring this, which again is not something we're doing right now, but something we aspire to do, to actually saying what dark matter is, what dark energy is? Well, it's a big cosmological inference problem. We can run simulations of the universe. I said, this is a simulation of the universe, and so we can set the properties of the physics at the beginning, run the simulation to the end, and tell us what kind of hydrogen signal that would lead to. And so you can use techniques like Markov chain Monte Carlo or machine learning to try and actually reconstruct the underlying properties that went into this image. But we don't have the real data, and our simulations will never be accurate enough to capture what's in the real data, not even just the telescope effects. Okay, let's pretend we corrected for all of those. Right, I said this is a gigaparsec on a side. To understand the physics of what's happening in the hydrogen signal on these scales, which again are really the scales the signal has a lot of features on, the driving force are stars that are putting out photons and affecting the state of the universe. A star is about 1 part in 10 to the 17 along this axis. If we wanted to do a first principle simulation where we have all the stars in this volume, we would need 10 to the 17 pixels on a side of a cube. Never going to happen. These simulations will always be approximate. And so then the question becomes is, the question becomes, are our approximations good enough? And the answer we seem to be getting is no, not yet. And so this is work from a collaborator of mine and a student working with him, showing here's a number. We might want to measure it from our data. It's not particularly important what it is. We'll call it tau. And it's using a convolutional neural net to recover tau from simulations like this. And what it's shown is if you, and these labels here, these are two different algorithms for creating simulated hydrogen signals. And so what this shows is if you take the Zeery ion algorithm, generate a bunch of simulations, put it in to your convolutional neural net, you get predicted taus that are in very good agreement, percent level, with the true tau. If you then take that network and give it simulations from 21 centimeter fast, another algorithm for making those simulated hydrogen signals, you get this bias. And there's a similar plot in this paper doing the opposite, training on 21 centimeter fast, predicting on Zeery ion, you get the same thing. These two approximate simulators don't generalize to each other. And so they showed in this paper that, well, if you make a mixed training set with simulations from both simulators, then you get a good result. But that's not going to take us to real data. Okay? Both simulators are wrong. It's not like one was right and one was wrong. One might be more wrong, but none of them are right. And so actually having something robust to the particular nuances of a simulation or the artifacts in a simulation that can generalize across all the simulations and then hopefully to real data, that's another hard problem. And so as I said, Jasper is working with Steve and I to try and come up with some ways to test generalizability and interpretability in this framework where we have these different approximate simulations. And so those are the three problems I wanted to highlight. Just to kind of summarize and lead us into the Q&A, right, as I said, we've been doing this for 15 years now, and we've not detected the hydrogen signal. It's not to say we haven't made progress, but progress has been slow. And so right now, I said the foregrounds are about 5 orders of magnitude brighter than the 21 centimeter signal. Right now, we've got about 1 to 2 orders of magnitude of residual foreground contamination in our analyses. So we've gotten 3 to 4 orders of magnitude down. But we're not there yet. And the last thing I wanted to say is, right, it's not like we've made no progress in all this time. We have these traditional approaches, and we continue to hone them. We continue to get better. Right? Every PhD student gets us another factor of 2. But that's not to say that fresh ideas aren't going to make a big difference. But there's a catch-up period, right? And so it takes, in some ways, a commitment to say, okay, here's a really valuable tool for this kind of problem. It's not going to solve it overnight. Right? You're not going to catch up to 15 years of progress. But I'm really ready to hear some fresh set of ideas because 15 years is also a long time. And so I'll leave it at that, and I think whether we go to questions or straight to discussion, I will leave to our host.
Thank you, Jonathan.
Should I shut this down so we're not blinded?
Well, that was fascinating. I learned a lot. Even some of the context from some of the things we've been talking about. It's awesome to see the big picture. Yeah. So let's start with questions. If anyone has a question for Jonathan, please raise your hand. Yeah, go ahead.
I have a question about kind of the theoretical detection of hydrogen. How much can it tell you about differences between stars? Like, would we be able to know the fingerprint for the sun relative to something else?
So yeah, I think that's one of the big questions we want to get at is how were the first stars in the universe different from stars today? And the signal in principle encodes all of that. because it responds to all the light emitted by all the stars in the universe. I chose my words carefully. It encodes all of that. It's sensitive to all of that. But it said it's not an easy, just read off the graph, oh, your stars were like this, as opposed to like this. But it's a very, very promising technique because nothing else has that cumulative sensitivity to all the stars. So something like James Webb Space Telescope is also peering back into these early epochs. But they're only seeing the biggest and the brightest and the rarest objects. They're seeing the tip of the iceberg, and there's lots and lots and lots of fainter galaxies that we expect to be out there that we just can't see other than studying their cumulative effects on the universe.
Carrie Ann.
Hi, I'm Carrie Ann. I'm a faculty member here in DSI, and so I work a lot with geophysicists. And one thing that always strikes me when I hear like cosmologists and astrophysicists talk, and I hear a lot from geophysicists, is like they always, to me as a data scientist, they're always kind of describing like the exact same challenges. And so like the geophysicists, like they're trying to understand what's happening under the surface of the Earth. They have sensors on the surface, and they're have like wave equation, all this sort of thing. And so I wonder when you're talking about like looking for new sources of ideas, like how much are astrophysicists and cosmologists actually talking to geophysicists? Like you're all kind of some different flavor of physicists, right? And I'm just curious, like, because I mean you could get ideas from like data scientists, computer scientists, but I just am curious like how much exchange is there between those disciplines?
I think it varies a lot, but generally there's not a lot of exchange. When you've been working on a problem for so long, it can be so easy to get into your niche and just have such a jargon that nobody else can understand. So if I'm talking to a group of radio astronomers who study star formation in local galaxies, our techniques are different enough that we don't even communicate in the same language. And so, I think, as you say, there's a lot of similarities, and it's always valuable to hash out that conversation and say, what are we doing the same thing? Or that's the same thing. And it can take a lot of time. I said, even though we're physicists, we are speaking different languages at some level. But you're absolutely right.
Sorry, I'm back here. Please.
I guess, could you explain why the telescope needs to be on Earth and whether you could get more information if you could theoretically have it
So,
on the telescope to the moon?
that's a great question. I am working with NASA to develop concepts for a telescope on the far side of the moon. I think the reason we don't start there is that makes everything more expensive and everything much harder. When you build your telescope on Earth, you can send your grad students to go and fiddle with the telescope when it's not working.
Suresh?
I think this relates to that question. Separately, I'm curious to what extent it's possible that sort of more multimodal approaches. Right, so you're trying to refine the telescope, refine the signal you're getting, hoping to get sort of subtract off these things so you can get some information about the hydrogen. Are there other telescopes collecting other forms of data that could, from a different angle, help you with this? Because I think in other parts of data science, multimodal techniques tend to work because they get at different sides of the problem and then they sort of carve out the signal you're trying to get. I have no idea if that even makes sense, so I guess that's a question.
Yeah, no, I mean, so there are several experiments all trying to do the same thing. There are other telescopes that are, their science are the foregrounds that we're trying to remove, and so they're helping to characterize those signals. And so there's definitely, a very traditional branch of radio astronomy that is building better and better and better models of the sky itself. That if we knew what the sky looked like to 1 part in 10 to the 5, we wouldn't have a problem with calibrating our telescope because we could just say, here's what it was supposed to look like at the level of precision that you need. It doesn't solve for your telescope response based on that. And so that branch of bringing lots and lots of astronomical data together to refine sky models continues to be a big source of progress, I would say.
But I meant in the case of the neural networks, right? They could take multimodal inputs and
I see.
get better at prediction through that process, is what I was thinking.
I see. As I said, it's an interesting idea. The telescope data has its own flavor depending on each telescope that it comes from. The reason we have 3 major experiments all trying to do the same thing right now is because we don't know how to build a telescope that can do this experiment. And so they take very different approaches. They have very different systematics. And so there's definitely, I think, potential to disentangle the same underlying sky with 3 different kinds of data sets. I think the challenge is that the ones in the northern hemisphere don't see the same data as the ones in the southern hemisphere. Actually getting a matched data set is tricky.
My understanding is that some of the reduction in noise is in some sense maybe not multimodal, but from like multiple viewpoints, right? So you were talking about the pairs of antennas and being able to see something that no individual antenna can see. And so like it almost struck me kind of like in machine learning where you would have maybe a multi-camera setup or something like that. And so to some extent, it seems like you're already doing some of that. Is that an accurate understanding?
No, I mean, I think traditional radio interferometry, which was invented in the 1940s by a bunch of bored British radar engineers after the war, right? The way they design their telescopes, any one pair of telescopes has a limited amount of information about what the sky looks like. It's sensitive to parts of the signal. The more antennas you build, the more of the signal you can reconstruct. And then you get into a trade-off between the data volume, because it goes as the number of antennas squared if we're correlating each pair. But if you can build more antennas, there's definitely a camp out there that says, let's just spend 2 orders of magnitude more money than you spent to date, build an enormous telescope where we're not trying to overcome the shortcomings of these medium-sized telescopes and their limited data, and everything will just fall into place. I think it hasn't gotten a lot of traction because dollars are hard to come by.
It's interesting. So one of the questions I had for you that I'd written down was, do you think we're more limited by hardware or software? And from your talk, and maybe this is just, because what I know of what you work on, I thought the answer was definitely software. Because you have all of this data that you've collected and you've got to, you're still after 15 years trying to get out the noise. But maybe it's not that simple a debate.
I think the hardware can make your job in software a lot harder or a lot easier, depending on how it's designed. And so that's kind of the experiment that we're doing. We've built 3, 4, 5 of these experiments, and every time it's iterate on the hardware to help alleviate the biggest problems we're facing in software, so that the software can then try and fix different problems. And so I don't know which the biggest problem is. I think we spend a lot more time on the software because that's what you can iterate on faster. Getting another $25 million to build another one of these telescopes only happens once or twice a decade, whereas changing your software, you can do that faster.
Did I see a hand in the back?
Yeah, I have the same question.
Oh, fantastic.
But I guess to what extent can the telescopes get better? Are they only going to get so good? Is it, because you're saying, I get the expense thing, but how much work has been done in that area to, can we make the telescopes better? I don't know.
That's a great question. I think what better means will be different to different people. We, in principle, have big enough telescopes and enough data sitting on a hard drive that if there was an enormous breakthrough on our way to analyze that data, we detect the hydrogen signal tomorrow. We're not limited by the telescope in that sense, that it's in principle capable of doing the experiment. What I ask is, can we build a more calibratable telescope? Can we build a telescope that has sort of fewer degrees of freedom required to model it, or is more stable versus time, so that we can have a longer baseline for consistency when we're trying to model it? And so I think those are harder questions to put a spec on, to give an engineer to say, I need a telescope that I can calibrate this well, isn't the same as, I need a telescope that kind of has this much sensitivity to a signal. But I think that's how we're starting to think about it for yet another generation of these experiments, is can we build something that gives us more tools to model it?
Here, please.
So, I guess it might be a silly question, but in this data that first actually you were showing us of where you kind of were able to parse out like ham radio outside of the frequencies that you're looking for, if you were to use that for like training these algorithms to try and figure out like and distinguish the information that you want, what is the dimension of that training time to use? So the axes seem like it's the frequency, so there's in a numerical aspect, but is there possibility of using like sound where like that data in a different mode?
Yeah, no, I mean, I think the first foray I had into machine learning was a grad student taking those pictures and basically treating them as inputs to a CNN to look for radio frequency interference. And it was 50 times faster than the algorithms we had. That was great. But we didn't have a ground truth to train it on. So I think until we have some way of knowing what is actually in the data to begin with, it's going to be hard to just do a kind of strong supervision. I don't know if that's where, it sounded like you were asking something a little bit different, but.
Yeah, I don't know how much it tracks to this, but like I thought about this famous scientist that, I forget her name right now, but she was cosmetologist too, but she's blind, so she tried to analyze everything not visually, and like she was able to make huge breakthroughs by just like listening to data instead of like actually looking at data. So it's like coming from that approach of like, is there a way to take the data you already have and you're looking at it from a different modality, like, or is it set in a specific format that this is kind of the only ability that you have?
I think we definitely have our traditional ways of looking at the data that are not the only ways to look at the data. And so, there are more than two dimensions to our data. And so just that kind of picture that I showed is definitely not the only way. So I think there's definitely, as I say, other ways to get at it. One of my colleagues did make some sound, turn our data into sound files, and now my 7-year-old is convinced that aliens are trying to talk to me, and I cannot convince him otherwise. They sound strange, but.
Rithamba?
So I have a question about the big data. So coming from a machine learning background, the idea is the more data we have, the better statistical power we have, the better we can train our models. But in your case, the challenges are so hard of the data that you're collecting. We don't have the ground truth yet, and we don't know when we'll have the ground truth yet, eventually. So then what is the intuition behind collecting more data at this point? Is it that once we have the ground truth, we'll know everything because of all the data that we have?
No, that's a great question. It's because we're changing the telescope. As the telescope changes slower than our ability to analyze the data. But if the telescope still looked the same it did in 2013, there would be no point to collecting more data. Some numbers that I've ran, so the current best measurement from the Murchison Wide Field Array comes from analyzing 400 hours of data. And it's about a factor of 1.8 better than my former grad student's thesis that analyzed 40 hours of data. You would expect an order of magnitude if we could just use the data and get everything we want out of it. And so we're absolutely limited by our ability to analyze the data and do something meaningful with it more than just having more. But I think, as I said, we are changing the hardware. And so the data from every year is hopefully getting better and getting easier to analyze.
Rhea?
Yeah, hi. I guess the question is a little bit muddled in my head now because it's a little similar to the numbers, but I guess
I think it's a question of not really knowing all the degrees of freedom in my data that I want to be able to marginalize over. The telescope parameters that I say are our nuisance parameters, in particular these gains, I can model them at the cadence of the data that we collect every half a second. They're probably not changing that fast. But if I put some sort of hard prior on it and say, okay, I'm going to only calculate them every 10 minutes, maybe I'm missing something. And so I think the biggest appeal is an approach that can take some sort of prior about physically, I think things should probably evolve on this time scale, but if the data are telling you that they're actually changing faster than that, if there's enough evidence to do something else. And so, Bayesian techniques use a lot of that language, but as I said, computationally, we haven't been able to get them to actually do that kind of marginalization over the high dimensionality space. And so, as I said, you're absolutely right. There's a lot of things that machine learning is not the right tool for. I said, I don't know if it's the tool here, but the idea of having a lot of nuisance parameters that I can't characterize a priori and trying to learn kind of their characteristics, their dimensionality, their time scales for variation directly from the data. Even if that's not the way that we ultimately determine them, just getting that kind of information about these nuisance parameters, I think, would help the more traditional approaches for calculating them.
On a related note, something that I'm always fascinated by about these problems is that you're in this world where there is no ground truth, and there's nobody you can turn to annotate the data. What is it going to look like when you get the hydrogen signal? Like, how are you going to know we got it?
So I don't have an answer.
Okay.
I thought a lot about this question. That's not to say that. As I said, we're marching this level of contamination down and down and down. And when your contamination is 2 orders of magnitude above any reasonable signal you'd expect to measure, you can say, oh, it's still contamination. When your contamination is at the level of a signal you might expect to be in your data, then we're really going to have a hard time saying we measured hydrogen and not foregrounds. And there are axes in which they discriminate themselves that we probably, with our first measurements, aren't going to have enough data to kind of do these jackknives where you'd say, okay, the foregrounds follow the Milky Way. And so if we analyze the signal when the Milky Way is up versus analyze the signal when the Milky Way is down, if we're getting different answers, that tells us it's systematic contamination. My guess is as soon as we cut our data set in 2 and try a jackknife test like that, we're not going to have a sensitivity to see the signal in either half. The first detection is going to be 2.5 sigma in 3 data points. And I think we're going to put it out there and hope that it turns out to be right a couple years later.
So it's not going to be some eureka moment where suddenly it's all there for us.
No, I think it'll be a lot of hand-wringing about, could this be it?
Checker.
So he this first. Okay,
There was a tie.
the approach, since you don't have a ground truth, assumes that you know all the contaminants. What if there are contaminants that you don't know that's coming from another source, cosmic source, not human source?
So yeah, I think the path over the last decade and a half has been, what's the tall tent pole this year? The tall tent pole, the biggest problem we have, try and solve that, take that approach as far as we can, and then things stop getting better. And then we kind of all get together and stare at our data again and say, okay, we seem to have bottomed out on our ability to improve things with that avenue. What's another approach? And we've discovered lots of things that we did not expect to be problems, just as we march down and march down and march down. There was a period 5 years ago when the biggest issue for us was that all the cables in the array had impedance mismatches at kind of the 1 part in 10 to the 3 level. And so we were getting reflected signals bouncing back and forth across the cables. And they're totally up to spec. Those are great cables by any engineering spec. But we're setting new specs as we go along. And so that, I think, there probably still are problems we haven't even identified yet that we'll need to solve to get to where we need to be.
Jane?
Yeah, I guess my question is very related to shapers, although I have another question if you've already answered it. But it's about simulations. So my field, studying genome-wide data in natural populations, also relies a lot on simulations. And we have fairly good generative models for genetic data in some sense from first principles of how cells work, but certainly we know we're missing things. Real data doesn't look like the data we simulate, but we have kind of made traction, and some people are now with things like GANs and transformers making more traction on what are the features that we're missing. And so I guess, I want to learn more about the simulations, and is it an inputs issue completely, or like is there a sense of some features you're getting right and other features that are not right?
Well, so I guess I'd ask, because there's two kinds of simulations we use. There's the ones I talked about where they're the astrophysical simulations. We're trying to make a signal that encodes as much of the physics as the signal in the real universe would. Then there's another branch I didn't talk about at all that I actually spend a lot of time on, which is making mock data, trying to make actual data that represents the sky. And so, as I said, I can write down the equation with no approximations that takes me from the sky to my data. And so we've developed a code in-house that's to compute that with no approximations is a high-performance compute issue. We can generate about 2 minutes of data in a day on Oscar right now. But so that's another aspect of simulations. And I think we're getting to the point where we're comfortable that everything that's on the sky in our input model is winding up in the mock data. And then it's a question of, all right, how do we start adding telescope effects? And not, the effects of the telescope are in there, I should say. It's mock data, but it's the perfectly known telescope that's in there. Start adding time variability, antenna to antenna variability. I think that'll be a very fruitful line going forward. We've had our missteps over the years as a community where analysis algorithms did unintended things that good simulations would have caught. And so I think there's a lot to be gained from that kind of work.
Could you also say something about the astrophysical simulation side? My understanding there is that it's primarily computational is the challenge.
Yeah, I think there are groups out there that try and do the biggest, most physically accurate simulations possible. And they publish a paper once every 5 years. And by the time they're analyzing their simulation data, some other experiments told them their inputs were wrong. So really doing the simulations at a high level of detail is a huge computational challenge. The approximate simulations, we call them semi-numeric, where you've used some type of analytical prescription to avoid doing some very, very detailed calculation. Again, 15 years ago when those simulations started first, the semi-numeric calculations started first proliferating, you'd see a paper like, okay, here's the signal from the approximate simulation, here's the signal from the really heavy-duty simulation. They're good to a 10%. Let's call this a day. Mm-hmm. And I think this question of generalizability has, in my mind, opened a new door into that question, that just agreeing with 10% isn't good enough if things ultimately disagree and you don't know why.
Mm-hmm. Any other questions for Jonathan?
I mean, that last point, the 10% thing, are there questions you could potentially ask about the origin of the universe that are crude enough that would still be useful there? I mean, is it that it sounds like in everything you're saying, the goal is to be as physically realistic as possible. The computer scientist in me is like, okay, suppose you approximate everything. You can still get some answers, and maybe that's okay, but I don't know if it's okay.
I mean, I think cosmology as a field was revolutionized in the 90s by the discovery of the cosmic microwave background that took the field from being pencil and paper to percent level errors. And now we're at sub-percent level errors on a lot of our key cosmological parameters. If there's something unexpected in the universe, we're probing an unexplored epoch of cosmic history. If something totally unpredicted is happening then, that could be an order unity change in the signal, and we wouldn't need a lot of precision to know that something is totally different than what you'd expect. But generally, cosmology right now is trying to get 1.0 plus or minus 0.01 to be 1.0 plus or minus 0.001.
Maybe I can wrap up with a question that kind of goes back to something that came up at the beginning of the discussion, which is you mentioned this having to hash out vocabulary, and that was more in the context of like different physics disciplines. But that's something that's also struck me about our collaboration, other collaborations that I've been involved in. I think we were on a call a couple weeks ago where we had different meanings of the word baseline, and we took but more broadly the vocabulary takes some of the work is just learning to have that shared vocabulary. And if there are students who are interested in doing this kind of work, they're interested in both physics and data science and whatever that intersection is, what advice would you have for them specifically about, and perhaps specifically about that navigating that vocabulary?
No, I first let me completely agree that progress, even when I talk to somebody working on another experiment trying to measure the exact same thing, the first 45 minutes is making sure we're saying the same things to each other. We've developed such a level of jargon that to us it's incredibly precise, and it's very important to be precise, but it's a total pitfall if a lot of these words have other uses than what you intend. And so, I think what I would say to a student more than anything else or anybody is, ask. What do you mean by that? When you've been using the jargon for so long, sometimes you forget which ones are jargon. Or sometimes you're embarrassed to say, actually, that's a word I introduced to the field 10 years ago, and I've regretted it ever since, and I wish we'd call it something else. But we're stuck with it. Just knowing that these conversations take time to actually establish a common vocabulary, and to not be afraid of, well, maybe another way, I get the sense a lot of people will come out of an initial conversation or a couple weeks of working in this where you're still going through the vocabulary and it feels like you've made no progress. That establishing the vocabulary is progress.
All right, well, thank you. Let's leave it there. Jonathan, thank you so much for coming.
Thank you again for having me. It's been a pleasure.